Have you ever thrown a ball into the air? You know it will come back down. It always does. This is a rule, a law of physics. It governs everything from the smallest speck of dust to the largest star in the galaxy. These rules seem solid. They seem permanent. They tell us how the universe works. They describe the dance of planets, the fusion inside stars, and the way light travels across the vast emptiness of space. We build our world on these rules. We launch rockets, design computers, and predict the weather, all because we trust them. But are they truly unbreakable? Is that even the right question to ask? This idea is both exciting and honestly a little frightening. Before we can talk about breaking the rules, we need to understand what they are. What exactly is a law of physics? It is not like a law passed by a government. You cannot choose to disobey the law of gravity. It is not a moral code. A law of physics is a statement, usually written in the language of mathematics, that describes a fundamental property of the universe. It is a pattern that nature follows consistently and universally. We do not invent these laws. We discover them. We find them hidden in the workings of the cosmos, waiting to be revealed through observation and experiment. The process of discovery is long and patient. So we stand at a fascinating crossroads. On one hand, we have the incredible success of science. The laws of physics, as we understand them, have allowed us to build our modern world. From the microchip in your phone to the satellites that guide us, our technology is a testament to how well these laws describe reality. We can predict the motion of a planet millions of kilometers away with breathtaking accuracy. We can harness the power of the atom. We have sent probes to the very edge of our solar system, all guided by these fundamental principles. Their power is undeniable. They work. On the other hand, there is a deep sense of mystery. There are things we still do not understand. What is dark matter, this invisible substance that seems to hold galaxies together? What is dark energy? What are physical laws? At their core, they are the patterns that nature consistently follows. They are not rules that were handed down by some cosmic authority, nor are they suggestions that can be ignored. Instead, they are descriptions of the fundamental behavior of matter and energy. Think of them as the grammar of the universe. Just as grammar dictates how words must be put together to form a meaningful sentence, physical laws dictate how particles and forces must interact to form a coherent reality. We do not invent this grammar, we discover it. We observe the universe speaking, and we try to understand its language, which, as Galileo famously noted, is the language of mathematics. For over 2 centuries, the scientific world lived in a reality largely defined by one man, Isaac Newton. His laws of motion and universal gravitation were not just scientific breakthroughs. They created a whole new way of seeing the universe. Before Newton, the cosmos was a place of mystery, governed by divine will or incomprehensible forces. After Newton, it transformed into a magnificent, predictable machine. It was a grand clockwork where every gear, from the smallest projectile to the largest planet, moved according to simple, elegant, and unwavering mathematical rules. The mystery of Mercury's orbit was finally solved by one of the greatest revolutions in scientific history, Albert Einstein's theory of relativity. Einstein proposed something extraordinary. He said that Newton's view of gravity as a force was incomplete. Instead, he described gravity as a consequence of the curvature of space-time. Imagine a heavy bowling ball placed on a stretched rubber sheet. It creates a dip, a curve in the sheet. A smaller marble rolled nearby will follow that curve. However, when we journey down into the realm of the very small, into the world of atoms and subatomic particles, the rules seem to change dramatically. This is the domain of quantum mechanics, and it is a place that, honestly, just defies our everyday intuition. Here, the comfortable, deterministic laws of classical physics give way to a world of probability and uncertainty. A particle like an electron does not have a definite position until you measure it. Instead, it exists in a superposition, a cloud of potential locations. It is not that we do not know where it is that it genuinely is not in any single place. Is this nature breaking its own rules? Given the unwavering consistency of physical laws, both large and small, why do we remain so fascinated by the idea of breaking them? Part of the answer lies in our hopes and our limitations as human beings. We are bound by these laws. Gravity keeps us tied to the earth. The second law of thermodynamics dictates that we age and that our creations decay. The speed of light confines us for now to our own solar system, making interstellar travel a monumental challenge. The laws of physics define the boundaries of our existence, and it is human nature to dream of transcending our limits. The dream of finding a loophole is a powerful motivator. It fuels science fiction with tales of warp drives. While we cannot seem to change the laws, their very nature presents us with a profound mystery. This is often called the fine-tuning problem. When we look at the fundamental constants of nature, numbers like the strength of gravity, the mass of an electron, or the energy of empty space, we find something remarkable. It seems that these numbers are set to incredibly precise values. If you were to change any of them, even by a tiny fraction, the universe as we know it could not exist. Life, and indeed any form of complex matter, would be impossible. The idea of a multiverse, with different universes governed by different laws, is a mind-bending concept. It takes the limits of negotiation to their ultimate conclusion. While we may not be able to change the laws in our universe, this idea suggests that other sets of laws are possible and might exist elsewhere. What would such a universe look like? Could life exist in a cosmos with a different set of rules? It is a question that pushes the boundaries of our imagination and our scientific understanding, forcing us to think about what is truly fundamental about reality and what might just be a local bylaw of our particular cosmic neighborhood. Imagine a universe with 2 dimensions of space instead of 3. Our journey has taken us from the familiar fall of an apple to the mind-bending frontiers of quantum mechanics and cosmology. We began with a simple, provocative question: can we break the rules of physics? The answer, it seems, is both a simple no and a wonderfully complex "it depends on what you mean." We cannot negotiate with gravity. We cannot bargain with thermodynamics. The laws as they exist in our universe appear to be fixed, non-negotiable pillars of reality. They are the grammar of the cosmos, the unyielding logic that allows for the existence of stars, planets, and people. We are not the authors of this rulebook. We are its students, slowly and patiently learning to read its pages. This might feel like a limitation, a cosmic boundary we can never cross. Yet, it is this very rigidity that makes our universe and our science possible. The unwavering consistency of these laws allows us to build knowledge, to make predictions, and to construct technologies that have transformed our world. The stability of the laws is not a prison, it is the solid ground beneath our feet. The true adventure lies not in breaking the rules, but in understanding them more deeply. We stand on a shore of knowledge, looking out at a vast ocean of mystery. We must keep asking questions, keep testing the boundaries, and keep looking up at the sky with a sense of wonder, always striving to better understand the magnificent and enduring laws of our universe.